Hello, students. Welcome to the physics classroom. And today we are going to discuss problems involving Newton's second law of motion. We are going to apply Newton's second law to answer several questions. Most of the questions can be solved using basic algebra. Some questions can be solved using logic. We can just use logic to answer the questions. Let's get started. Question number 1 says, Tamika pushes a heavy box horizontally on a level floor. Unfortunately, the box does not move. How great is the force of friction on the crate compared to the pushing force? Here, we need to understand that the phrase, the box does not move, is very, very important, because it tells us that the acceleration in the x direction is 0. In other words, we have no acceleration in the x direction. Now recall that second law tells us that the net force in the x direction must be equal to mass times acceleration in the x direction. And for the fact that acceleration in the x direction is 0, this gives us mass times 0, gives us the net force in the x direction is 0. In order for the net force to be 0, then we should have balanced the forces acting on the box. So we have actually balanced the forces. That's what we see here. Balanced forces is what we have in our case here. Balanced forces. Okay, so we have balanced forces. Balanced forces means that the pushing force must be equal to the frictional force. So to answer the question, how great is the force of friction compared to the pushing force? They are equal. They are equal in magnitude. So they are equal in magnitude. Okay, you can also show this by understanding that since the net force in the x direction is equal to 0, then it implies that this net force must be, we have to draw the force diagram always, it helps. This is the surface, this is the object here. There is a pushing force, we call it P, and there has to be a force of friction acting in the opposite direction, F. Now, to understand the net force in the x direction means that I have to have P, which acts to the right. It has a positive sign, but I don't include it. Then we add with another force of friction is acting to the left, so minus F. The result must be 0. And here, positive times negative is negative, so P minus F equal to 0. Indeed, the pushing force is equal to the force of friction. All right, so this marks the end of question number 1, discussions. It is always important to underline important phrases that will help you to answer the question and to remember how to apply the laws of physics or Newton's second law to answer the question. Question 2 says, if Tamika increases the push, will force of friction on the box increase as well? Well, there are 2 cases here. Case 1 would be the object still at rest. Sorry, there are 2 cases here. So case 1, the object will be at rest. Object still at rest. Object still at rest. If the object is still at rest and Tamika tries to increase the pushing force, maybe it's now larger than before, then the frictional force has to balance that. The pushing force is the frictional force. Because what we need is that the acceleration still has to be 0. The object is at rest. Still, the acceleration has to be 0 meters per second squared. No acceleration. and therefore we should still have balanced forces. I'm sure you have encountered this situation before. You push a refrigerator, it doesn't move. You push it harder, it still doesn't move. You have pushed a crate before, a crate on a level surface. You see this happens all the time. The moment you increase the pushing force, friction also increases to balance this, unless we have some motion. But as long as the acceleration is 0, then P must be equal to F, right? So again, here, P is equal to F. In other words, pushing force equal to a friction force. And now there's another case whereby the box moves. The box moves. It is possible that Tamika will be successful in the long run, and the box moves from rest position. So what will happen? In this case, we know that there is initial velocity of the box is 0 meters per second, and V final, once the box starts moving, well, we don't know, but it'll be something, but it will not be 0. Now, if we have this case whereby V initial is 0 and V final is not 0, then we have some acceleration there. So there is acceleration. There is acceleration. There is acceleration on the box. In other words, the box accelerates. Now, according to Newton's second law of motion, if the box accelerates, then there is a net force. Consequently, there is a net force in the x direction. In the x direction. So if we are saying that there is a net force in the x direction, and there is acceleration, positive acceleration in the x direction, then in this case, we can say that P must be larger than the frictional force. In other words, the case, in order to move the box, must look like this. The pushing force must be larger than the frictional force. This is a P, and this is a frictional force. In this case, we are going to have a net force, and that net force will accelerate the box to the right. Okay. Now let's look at question number 3. Question number 3 says that let's triple the mass of a sliding block. At the same time, triple the net force acting on it. Compare the new acceleration to the original acceleration. Newton's second law will help here. I can write my original acceleration, A0, equal to net force, and this will be original net force. Original net force, let me write that one as follows. So this is the original net force divided by original mass. Now, in the new acceleration, new, it will be the net force, and this will be new net force divided by the new mass, or that'll be the new mass. Let me fix that. So this will be the new mass new. Okay. Now we are told that the new net force here is actually 3 times the old net force. So we can rewrite acceleration new as 3 times the old net force, original net force, divided by 3 times, we also triple the mass, 3 times m0. And here we can see 3 and 3 cancel out. We end up with the same result here. The net force original divided by mass original. Now this looks like actually our original acceleration. This is the acceleration original. In conclusion, we see that the acceleration original, the original acceleration is equal to the acceleration new. No change in acceleration. So to say, no change in acceleration. Let's move on to question number 4. Question number 4 says, determine the weight in newtons of a person who has a mass of 60 kilograms. Weight is defined as mass times acceleration due to gravity. Our mass is 60 kilograms, and our G is 9. We use 9.8 meters per second squared. If we multiply the two, we get 588 and kilograms meters per second squared. We usually represent a kilogram meter per second squared by a newton. So that would be 588 newtons. So that will be the weight of the person, 588. These questions, we would like to find let's see, the net force and the acceleration. Remember, the net force is given as follows. We add 10, takes a positive sign because it's acting to the right. And this one takes a minus sign if I add it, minus 5 newtons, because it's acting to the left. The result will give me positive 5 newtons here, positive 5 newtons. So the net force is 5 newtons. If I want acceleration, I need to remember that it's the net force in the x direction divided by the mass. And acceleration will be actually 5 newtons divided by 5 kilograms, because the mass is 5 kilograms here. The result will be 1 meter per second squared. Okay, we are going to do this for each situation below quickly without going through all this trouble here. We can just quickly answer the rest of the questions. For example, situation B, our net force, we do the same thing as above, will be 15 plus minus 10, same as 5 newtons to the right. So I put a plus here. And acceleration, if I divide the net force by the mass, I'll end up with 5 newtons divided by 5 kilograms. So here it looks like we have the same acceleration, 1 meter per second squared. Okay. We can do the same thing for part C. Part C, we do the same thing. The net force happens to be what? Can you guess? Net force would be 5. If you said 5, thank you. 5 newtons. And then the acceleration will be net force divided by the mass. Net force in the x direction divided by the mass. That gives you 5 newtons over 10 kilograms. That will be 0.5 meters per second squared. Likewise, situation D, we can go ahead and do the same thing. We can find the net force in the x direction will be 5 as well, plus 5. And then acceleration, you can tell that this time around it will be, if you look at the net force divided by mass, our net force is 5 newtons divided by 20 kilograms. That will give you 0.25 meters per second squared. Per second squared there. Okay. Trying to put a squared there, but I don't know if you can see it. Okay. All right, so that will be our acceleration. Okay, so we can see here that acceleration depends on the mass. See, we had the same net force, 5 newton, 5 newton, 5 newton. So basically the acceleration here for the same net force, we see acceleration depends on the mass of an object. And as we can see, the larger the mass, the smaller the acceleration. So you have a small acceleration for 20 kilograms object, and we have a larger acceleration for the 5 kilogram object over there. Okay. All right, question 6. A train travels along a horizontal level surface at a constant velocity. What is the horizontal net force acting on it? Well, we know that the net force, according to Newton's second law, is mass times acceleration in the x direction. And since they tell us that it's moving at a constant velocity, it means acceleration in the x direction is equal to 0 meters per second squared. So this becomes m times 0 meters per second squared, and this gives us 0 newtons. Therefore, the net force in the x direction is 0 newtons. 0 newtons. That's why the passengers are comfortable when the train is traveling at a constant velocity. Passengers are not comfortable when the train is accelerating, speeding up or slowing down. Passengers are not comfortable. They can only be comfortable if they are in a situation whereby the net force is 0. All right, let's look at the last question. Is it possible for an object to be in free fall while going upward from the ground? Explain. Well, we need to understand the definition of free fall. Free fall in physics simply is defined as motion under the influence of gravitational force only. It is defined as motion under the influence of gravitational force, under the influence of gravitational force only. No any other force, but gravitational force only. Only. So that's the definition. But is it possible for an object to move upward under the influence of gravitational force only? Yes, if we ignore air resistance, any object that is tossed upward, once we release, once we are no longer touching it, if we ignore the influence of air resistance, the object is in free fall. It loses speed as it is going upward, of course. Most students think that free fall only relates to falling towards the ground, but that's not the case. Objects can be moving upward. They can be following a parabola like this, parabolic motion, or they can take different paths. As long as the only force is gravitational force only, then we say that the object is in a free fall. The question is free from what? Free from any other forces like air resistance, pushes and pulls. It is free from those forces, but it's not free from gravitational pull. It is actually not free from gravitational pull. It is free from outside influences other than gravitational force. Falling is kind of confusing. We know that in everyday language, falling is associated with going towards the ground. Like if you drop an object from a roof of a house or from a cliff, we see the object going towards the ground, and that's what we call by fall. But in physics, that's not it. This should not be something that can confuse you. You have to stick to the definition as it is used in physics. All right, we'll stop here. If you have any questions, please let me know. I'll keep these answers. Okay. All right. So this marks the end of our discussions, and thank you for your attention. Bye-bye.